Hey guys, welcome to day 7, transformations of logarithmic functions. Okay, we're going to start by looking at graphing log functions and discussing their domain, range, intercepts, and asymptotes. Okay, so let's go ahead and begin. A quick review, we're going to look at 10 to the power of x, and then we're going to compare it with its log of x inverse. Okay, so over here in Desmos, I've created 10 to the power of x in red, and I've shown that log base x of x, log base 10 of x is this green function. So a couple things to note right off the bat. They are inverses of one another. In other words, they are reflecting across y equals x, if you will. So you could fold it over like a piece of paper and one would become the other. Remember with inverses, when I'm switching the x and the y's, I get the other graph, okay? So another thing to note is that this log of x is actually log base 10 of x. So what I'm going to be looking at are these two functions where this log has a base 10. Okay, so if you don't see anything there, it's understood to be 10. Just like if I put square root of 4, well, and I asked you what's understood to be here, you would say 2. But we don't write it. We just understand it as 2. Okay, and if it was 3, then it is the cubed root of 4, which would be weird. We don't know the cube root of 4, but we know the cube root of 8, which would give us 2. Okay, so that's what's going on here as far as it's an understood 10, but it doesn't have to be written. But notice the reason why it's understood as 10 is because it's the inverse of our 10 to the x exponential function. Again, a big reason why this is 10 is because we have 10 toes, 10 fingers. It's just the unit of measure that we've chosen to count by as far as in regards to exponential and logarithms, okay? So domain, we're going to look at the domain just real quick of kind of a small review of this 10 to the power of x. Okay, so if I come back here and I look at this red function, 10 to the power of x, the domain is, of course, all real numbers. And you could put that as negative infinity to positive infinity if you want it as well. Okay, so oops, I don't want to leave the site. Let me come over here, which is what we have here. The range is 0 to infinity. Okay, so it doesn't quite hit the x-axis, but it does immediately happen afterwards. So we're going to say y is greater than 0, otherwise 0 to infinity. These are x values, remember, that it doesn't touch. Okay, the x-intercept. Did this red graph hit the x-axis? It never does. It gets very close to it, but it never does. So we're just going to put does not exist. Okay, and then the y-intercept. It does hit it at y equals 0. So you could put it as a point, or you could put y is equal to, not 0, y is equal to 1. Okay, this 1 is what we're talking about. This value is what the y value is equal to as a y-intercept. And then last but not least, the asymptote. This red exponential graph, 10 to the power of x, has an asymptote, but it's a horizontal asymptote. Okay, so we're going to go ahead and write that in. It's a horizontal asymptote, and it's the equation y is equal to 0. And this is like if I had my x and y axis here. Again, we're looking at this exponential function like this. This y equals 0 bit right here is going to be this right here. So this horizontal asymptote of y is equal to 0. Let me make that a little bit cleaner. So right off the bat, notice that we have a y equals something and a y equals something here. One represents a line that the graph will never touch, and the other one just represents a y value. So make sure that you know what context these y equals are referring to, okay? Because they can get confusing. We just have to know what they represent. All right, so now let's move on to our new function. Like I said, log base 10, which it's not written, it's understood. So log of x, it's called the common base, by the way. So if it's not written or there is a 10 there, this is called the common base. Okay, and again, it's common because we have 10 toes, 10 fingers, that's how we count it. Since these are inverses of one another, and we saw that from the graph, we know that what used to be the range is now going to be the domain on this new one, okay? So it's going to be x is greater than 0, otherwise 0 to infinity. Okay, all we did is like we flip-flopped those two. Okay, And then the domain kind of is going to become the range over here. That's what's happening as far as inverses go. So the domain will become the range of all real numbers, otherwise negative infinity to positive infinity. And then the x-intercept, yep, is going to come from what used to be the y-intercept over here. So, and again, we have to keep track of flipping the x and the y. So it's going to be 1, 0. And then this one will become the does not exist part over here. And then the asymptote. This is where it kind of is the same, but we have to flip-flop for inverses. So when we flip-flop for inverses, just remember the x and y's flip-flop. That's the big conceptual understanding of what's happening with inverses. So we're not going to have a horizontal asymptote. We're going to have a vertical asymptote. And it's going to be x equals 0. Okay? And again, from the graph, the log of x look like this, and it has a vertical asymptote at x is equal to 0. That's what's going on here. Okay, so quick attributes, that's what's the differences between both of them. But I do want to make sure that you understand that there are key points to these graphs. The y-intercept is a key point. It's like a pivot point that we use like with transformations. It's at 0, 1. And then 1, 0 is a pivot point. It's a key point of 1, 0 here with the log of x, okay? And yes, just to show you what these key points are showing, the key point would be if I plugged in this 0 right here for x, well then we know 10 to the power of 0 is equal to, let me highlight it in blue, would be equal to 1 that you have over here, okay? And the key point over here is if I put in this x value of 1 here for x, well then it would give me a value of 0 out here, okay? And the reason of that is this right here is log base 10. It's known as the common log. And let me go ahead and plug in this 1 value here. So let's say we didn't know what this equaled. Well, 10 to the power of something is 1. Best way to find a logarithmic is to rewrite an exponential. And the only way that that something could happen is if this something was 0. Okay, so that's what's going on there. Just a little quick history on that. All right, so now let's look at what are the graphs. So we saw the graphs already from Desmos. We saw them. And if I wanted to plot them as far as points, I'm not going to regraph them per se as slowly. I'm just going to go ahead and show you what points are key. Okay, so we're going to go right here. And this f of x, we're going to list, first of all, 0, 1, that key point. And over here, this is 1, 0. Okay, again, this is log of x. And this one was 10 to the power of x. So this is the exponential. And this is the logarithmic. Okay, so if I have 0 here, it would yield 1. If I put 1, it would have 10. If I put 2, it would have 100 because 10 squared is 100. And if I put something like a negative 1, I'd have 1/10. Okay, so at negative 1, I have 1/10. At 0, I have 1. At 1, I have 10, and so on and so forth, to where this graph looks something like the following. Just a quick sketch. That's 10 to the power of x. And yes, it does have a vertical asymptote right here. Sorry, a horizontal, that is, at y equals 0. So horizontal asymptote that we said way up here of y is equal to 0. Okay? And then we also have this one over here that we could have 10. Again, what I'm looking at are flipping these values because they're inverses, and 100 would yield 2. And just like this would be 1/10 yields a negative 1. So 1/10 at negative 1, 1, 0, and 10, 1. This is the graph. Slowly grows. It very, very slowly grows, but it does grow forever. And then this is what that graph will look like. Okay, so those are just the table values. Just wanted to show you real quick. And just to remember that this has a horizontal asymptote of y is equal to 0. When I didn't draw it on this one yet. And this one has a vertical asymptote at x is equal to 0. All right, so let's keep going. The next slide we're going to be looking at are a couple different equations. This one, it's not the common log. This is log base 2. So again, remember, this is normally 10, but it can be other numbers as well, including e, okay? So log base 2 of x, we want to see what would those values be as far as a graph, okay? So what I'm going to do is I'm going to quickly create an xy table. Oops. And I'm going to plot some points, okay? So this log base 2 of x is very close to log of x, okay? The only difference is we're going to see how does it jump by each jump, okay? So in other words, some values that we're going to look at, whoops, let me change that, are -2, -1, 0, 1/2, 1, 2, and 4, okay? Now at -2, it does not exist. We're going to say D and E. Does not exist here and does not exist here. And the reason of that is that this shares a lot of attributes with log of x. It doesn't ever hit the y-axis because that's the vertical asymptote of x is equal to 0 that it's approaching, okay? But then it does exist immediately thereafter, okay? And we're going to plug in these values to see what would we get as a y value. So if I'm plugging in these values, this is going to go for x. Again, if I use the reverse Hart method, let me show you real quick. Log base 2 of x is equal to y. I'm plugging in this gray value of 1/2. Okay, that's the same as saying 2 to the power of y is equal to 1/2. So 2 to the power of something would give me 1/2. And that would be a -1 because 2 to the -1 is understood to be over 1. And it could be written as 2 to the +1 if I move it downstairs. Because remember, we've talked about this with radical functions and radical exponents. Sorry, when we're doing radicals, we're talking about negative exponents. We move it and then we make it a positive when we've moved it across from the numerator to the denominator, vice versa. Okay, an understood 1 already exists there. That's how we get this 1/2. So that's what's going on here as far as to show you that we get a -1. Okay, so now in this equation right here, if I put for x, if I put a 1, then I'm asking myself 2 to the power of something is equal to 1. Okay, so that would change this to a 1, because again, let me highlight that better. Remember, this is 2 to the power of y is equal to x. And now if I put this 1 here for x, then 2 to the power of something is equal to 1. Well, it'd have to be 0. Okay, so this would have to be 0 in order to make that 1 work. Okay, again, the reason why this is a little bit different is because I'm using the exponential function kind of to verify what these values are from the table. Okay, so let me go ahead and show it with highlight as I go, because this can get a little bit confusing. If I go ahead and plug in 2 for my x right here, that's the same as plugging 2 in for the x here. We're going to see what does it spit out as a y. Well, you don't really know this like you don't know log base 2 of 2 just as easy as if you were to put this 2 over here where x belongs and then ask yourself, what would y equal in order to make this 2 to the power of y equal this value of 2, okay? And the only thing that would work with would be 1. So that's how we get 1. Oops. Let me do it like this. That's how we get 1 for our y value over here. And then last but not least, if I plugged in 4 for x, which again is here, but it's easier to see it in exponential notation, I could see what I'm going to get as a y value here, because 2 to the power of something equals 4. Well, that something would have to be 2. So this is how I can get these values. I'm using the exponential function as a tool with that reverse Hart method rewrite in order to graph it if I did not have a calculator. Now, if I did have a calculator, I could go quickly to, let me go ahead and show you. I could store this log base 2 of x function. So come here, grab the log base 2 of x, and we would store it as f of x. And now I can get these values by putting in 1/2, 1, 2, and 4. Okay, let's go ahead and put, oops, in the calculator. We'll say f of x, f of 1/2, f of 2, f of 4. And notice we got -1, which is right here, and then 1 and 2, which are here. Okay, the only one I haven't done yet is what is the value at x is equal to 1. So what would f of 1 be? And you see that we get 0, just like it was verified here. Now, -2, -1, and 0, again, those are to the left, which we can't take the log of a negative ever. We also can't take the log of 0 ever. So if it's in parentheses as a negative or 0, we can't do it because the default domain of these logarithmic functions are going to be, this is very, very important. This is how you can check for extraneous solutions and stuff like that at a later time. It can only be positive x values. Okay, so let's go ahead and come over here and we're going to go ahead and show you that -2, -1, 0 would not work. Okay, we already know from the graph. We already know over here that it doesn't work, but I'm going to show you from this right here of what we have stored. So if I put -2, it gives me this error. Square root of -1, it's imaginary number, so it doesn't work. Okay, if I put f of 0, it has undefined. So anything negative, it shows it as imaginary, but 0, it shows it as undefined. So the difference there is they both don't exist. The only difference is that 0, it says undefined because there's a vertical asymptote. Okay, so now let's keep going. We are going to use this function. Okay, so this right here, just so you know, this we've already plotted in the previous slide, so I'm not going to replot that one. I'm going to go ahead and save time and go straight to example 2. Okay, in example 2, I'm going to use log base of 2, which is up here of what we just graphed. Oh, I got to finish graphing this. So 1/2 is -1, 1, 0, 2, 1, and 4, 2. This is what the graph looks like. Okay, and I'm going to take this graph and notice that the only thing that's different is this +3 and this +1. Now, just like before, everything in parentheses, which is right here, is going to be horizontal change. All the things that are outside of parentheses, like over here and up front, are all going to be vertical change. So what you see here is a horizontal shift 3 units, not to the right, but to the left, because it's opposite with the x. And you also see 1 unit up as far as a vertical shift. Okay, so let's think about this. If I shifted everything 3 units to the left, one important thing that you have to know right off the bat is that you shifted the vertical asymptote of x is equal to 0 to now x is equal to -3. Okay, now everything else is going to shift 1 unit up. Okay, so everything shifts 3 units left and 1 unit up. So that means this point right here, which used to be at 1/2 -1, is going to shift 3 units to the left and 1 unit up. So 3 units to the left and 1 unit up is now going to be at -2/2, 0. Okay, let me do that point by point. Now this 1, 0 is going to shift 3 to the left, so it's -2, 0, and then 1 up, so it becomes -2, 1. Now this next one here is going to be 2, 1, which if I shift 3 to the left, is going to be 1, 2, -1, 1, and then I shift 1 up, so it'd be -1, 2. Okay, and then so on and so forth without showing it. Now you could also do this. It went up 2 and over, or up 1 over 2. And because there were only shifts, you could go up 1 over 2 and come up with this point right here. And I have this graph. Okay, so this right here that I just graphed is this transformation right here. The domain is no longer x's that are greater than 0. This one's x's that are greater than -3 or -3 to infinity. And the range is still all real numbers, as it will always be. And the asymptote is going to be x is equal to a -3. Okay, so now let's move on to this one. So this one is a natural log function. I'll tell you right now, just like we saw this one as a base of 2, the natural log could also be rewritten as log base e. So when you see log base e, it's the same as just writing the natural log. So if I had log base e of x, this is the same as the natural log of x. Because again, this, wherever you see it with the base of e, is the same as that natural log. Okay? So if this is natural log of x, and I want to find the horizontal shift, so on and so forth, I need to first graph the natural log of x. So let's come over here and graph the natural log of x. Well, just like we had 10 to the power of x, its inverse was log of x. This one comes from the fact that we have e raised to the power of x. These are inverses of one another. Okay, I just showed you log base e is equal to natural log. That means that these as functions are inverses of one another. Okay, they both reflect across y is equal to x. So what I'm going to do is I'm going to take the natural log of x, which is this graph right here, and I'm going to shift it 3 to the right. Okay, so we're going to say horizontal shift 3 units right. Again, because we're doing the opposite. This one is just 2 units down. Okay, so when I come over here, we'll see that this does in fact move 3 to the right. And then I will subtract it. You know what I'll do? I'll show you with this original one. And then I'll say natural log of x minus 3. You saw it shift to the right. And then minus 2. You saw it shift 2 down. Okay, so that's what this one's going to look like over here. As far as the shifting, as far as the moving and stuff, that's what we're going to get whenever we do the transformation. Okay, so the parent function, again, was natural log of x. Let me go ahead and draw that right quick. The parent function was natural log of x. And let me show you what that looks like. So natural log of x is 1, 0, and then 2.718 at 1, and it looks something like this. That's the natural log of x. And we got that from this black graph right here. Okay, for the sake of time, I'm not going to plot all these points. I'm just going to show you the natural log of x. So now in red, we're doing this. Everything got shifted 3 to the right and 2 down. Okay, so oops. So let me go ahead and move point by point. So this one got 3 to the right. So 1, 2, 3, and 2 down. That one went here. Okay. And then now this point right here, let me highlight it. This is 2.71828. That's that E value. Got shifted 3 to the right. So that's at 5.7 and then 2 down. So about here, but then 1, 2 down. Okay. And then again, what used to be the vertical asymptote at x is equal to 0 has now shifted to this right here at x is equal to 3. So that our new graph that we've shown is going to be this transformation right here. Okay, so the domain of this looks like x is greater than 3, otherwise 3 to infinity. The range is still all real numbers, and the asymptote shifted. So now it's at x is equal to 3. Okay, so now let's go one more slide. We're going to look at a couple of these, not necessarily all of them. Let's look at what we're trying to do. We're trying to graph our parent function. Our parent function is log base 2. Okay, and we've already done that back here. Okay, right here is this log base 2 with these values. Okay, and what we're going to do is we're going to shift these or do transformations of these. Okay, so I believe there's a mistake on the key. I think that this should be log base 2 as well, to match log base 2, to match log base 2, and to match log base 2. So go ahead and take that as an interpretation. Then we're going to graph the equation listed on each graph and describe the transformations. Okay. All right, so let's go ahead and look at the only thing different. If this is my parent function and I highlight that piece over here in all of these, okay, I can see that there are some transformations that are going to exist. Okay, this one is straight up just horizontal. So this is a horizontal shift 4 to the right. Again, because of the interpretation that everything with the x is horizontal and it's the opposite. Okay. And then this one right here, this 2 is with the x. It looks like a stretch. It looks like it wants to be a horizontal stretch because 2 is bigger than 1. But we're going to say this is a horizontal compression. Not by 2, but by 1/2. And then this one over here. This had 2 going on. Remember, log base 2 of x is my parent. So I have 1 here and 1 here. So we're going to say a vertical reflection, or otherwise reflects across the x-axis. And that's 1. Our second one is a vertical compression because 1/2 is less than 1. And vertical, we follow the rule. So vertical compression by a factor of 1/2. Okay, so real quick, what I want to do is I'm going to come over here and I'm going to copy this table just real quick. Okay, and I'm going to go ahead and put it over here so that you see where these values are coming from. So let's go ahead and paste. Whoops. This right here. Okay, so this is our, again, this is our log base 2 of x function. Okay, and now what we're going to do is we're going to shift all of these. So let me go ahead and draw what that looked like also, just real quick on all of them. So we have 1, 0, 2, 1, 4, 2. Okay, 1, 0, 2, 1, 4, 2. That was the parent. 1, 0, 2, 1, 4, 2. And then finally over here, 1, 0, 2, 1, 4, 2. Again, all of these have a default vertical asymptote of x is equal to 0, otherwise the y-axis. But I'm not going to draw that just yet. I want to do the transformation and then draw that, okay? So this is where they're coming from, guys. This is the parent function log base 2 of x on all of those. So now let's graph this function here. So everything gets shifted 4 units to the right. So let me graph this in red, okay? So 4 units to the right, this will go to 5, 0, and 2, 1, 1, 2, 3, 4, 5, into 7, 1, and so on and so forth. So because I got shifted 4 units to the right, what used to be the y-axis as an asymptote is now going to go 4 units to the right. Okay, so 4 units to the right, there is my new vertical asymptote. And we're going to call that x is equal to 4. So the graph looks something like this. That's the new graph. That's this transformation graph. Okay, over here, this horizontal compression, all these values, if you will, got multiplied in half. So we knew that it started existing here. So now it's no longer going to be at 1/2 -1. It's going to be at 1/4 -1. This will be 1/2 0. This will be 1 1. And this will be 2 2. Because all these values in the x are going to be horizontally compressed. It looks like they're multiplied by 2. It looks like that, but they're actually multiplied by 1/2 because of that interpretation of a compression. So this becomes 1/4 -1, 1/2 0, 1 1, and 2, 2. Because again, all those x values got multiplied by a half. That's what's going on here. So if I graph this, we'd have 1/4 at -1. And I know I didn't necessarily draw this enough to have room, but it would be 1/4 is -1 about here. 1/2 is at 0, 1, 1, and then 2, 2. And a horizontal compression kind of squeezes it even closer, tighter to that x-axis, and it almost looks like a vertical stretch. Horizontal compression almost looks like a vertical stretch. So our intuition is, in fact, realized and shown from the parent to the new function. Okay, and yes, this one still has a vertical asymptote at x is equal to 0, because there were no shifts. It didn't shift. There were no +3 or +8 or -4 or anything like that, like there was over here. So no shifts means the domain stayed the same. No horizontal shifts, that means. Okay. And let's see. The other one, the last one, is going to be a reflection across the x-axis, and then a compression vertically by 1/2. Okay, so let me go ahead and copy this one over here so that I can show you what's happening. And I will paste it here. And just real quick, so that we know what's happening with these values, what we're going to do is we're going to reflect these across the x-axis. That means all these y values are going to be multiplied by negative. So we'll have 1/2, 1, 2, 4 will become a +1, 0, -1, -2. This is from that first transformation that occurred. Okay, reflect across the x, that means the y values got multiplied by a negative. And then we're going to vertically compress this by 1/2. So we're going to take these values, and now these are still the same. So we're not doing any horizontal changes, but now we're going to vertically compress this by 1/2. So all these y values are going to be multiplied by 1/2. So this becomes 1/2. This is still 0. This is a -1/2, and this would be a -1. So 1/2, 1/2 is going to be about here. 1, 0 is going to be about here. 2, -1/2, and then 4, -1. And it looks something like this. Okay, so it's an inverted, if you will, logarithmic function. Okay, and notice that there were no changes. It did not add or subtract as far as the x values go, so it does still, in fact, have this vertical asymptote at x is equal to 0. All right, and then now, last but not least, the last slide. We have a couple more that I'm just going to show you the transformations, and you can, just for the sake of time of this video, you can plot these into Desmos and make sure that you understand what the table values would look like, and so on and so forth. Okay, so again, all of these are log base 2 as a parent function. Log base 2 of x. This is where it defaults. So this is the default, this is the default bare bones, and this is the default. Okay, so this one has x, and it also has y. So the way we're going to do this is, remember, we're going to do left to right inside of x first, then we come outside and do left to right as far as the y values are concerned. So if I were to write this like we've done before, a and b and c and so on and so forth like that, it would look something like the following. And we're going to do this also in B, C, A, D order. Okay, that's the order that we're going to interpret all of these. Remember, these big old parentheses right here are right here. This B is like a coefficient of this factored term, and we've talked about that as far as wanting to make that a +1 in units past. But nonetheless, our default is log base 2. Okay, so whenever I go over here, I'm going to do this value first, the x value. So we'll say the first transformation is a horizontal shift 2 to the left. Then we'll do this negative value. Notice that it's not in the parentheses, it's outside with a y value. So it's a vertical vertical reflection, otherwise reflects across the x-axis. Again, I'll let you use Desmos to see what these in fact look like. Number 5, we're first going to deal with this 1/2 that's inside with the x. So we know it's horizontal because it's with the x. It is multiplied by 1/2. Okay, so it's a stretch or compression. 1/2 at first glance looks like a compression, but we are doing the opposite with horizontal. So it's not going to be a compression, it's going to be a stretch. And not by 1/2, but by the flip of that, the reciprocal. So a stretch by a factor of 2. And then this 3 is simply going to be a vertical shift 3 units up. And then last but not least, this one down here has a lot going on. Okay, we're going to start with x. Remember, BCAD order. This one, if I were to rewrite this, it's the same as having -3 log base 2 of x plus 2 and then plus 1. That's the same thing because this is a positive one, so we're going to put a plus. And doing it in the order that it's shown here, we would list, first of all, this 2 was a horizontal shift 2 units to the left. Again, opposite with x. The next thing we see is this negative, then the 3, and then the plus 1. So let's do that negative first. Well, this is not inside parentheses. When I say not inside parentheses, I'm talking about these parentheses. So we know it's vertical, okay? So it's a vertical reflection, reflects across the x-axis. And then this 3 is a vertical stretch because it's bigger than 1, and you follow the rule with vertical by a factor of 3. And then last but not least, this was a vertical shift 1 unit up. Now again, I want you to look at Desmos for the sake of the time of this video. I don't want this video to be too long, but the biggest thing that I want you to kind of take note of is that this has a horizontal shift 2 to the left actually. So I know I put an arrow showing to the right, but this is 2 to the left, which I did show over here. Okay, so that means it's going to shift 2 to the left. That's where those shifts show where the vertical asymptote, which is very important, is going to move to. So that's the only thing that I'll show here. -2. And then this one did not shift because there was no addition or subtraction going on, just multiplication. So that vertical asymptote remains x is equal to 0. Again, everything else I'll let you look at, but I wanted to bring light to this. And then last but not least, this one moved again 2 to the left, which we showed here, which big time is important with that vertical asymptote, is going to show that x is equal to a -2. Everything else, you should be able to look at Desmos and or your graph on your graphing calculator. All right, so that's it for this first video.